So, first of all, in the last lecture, we derived, Navier-Stokes equation from conservation of linear momentum, right? And then we use, the linear relationship between stress and strain, and then we use something like this, right? Okay, so this is a shorthand notation for stress, and here I use a subscript. For example, ij. These are the numbers, and if you have 1, 2, 3, this corresponds to x, y, z. Okay, and then when you have u1, u2, u3. These are the u, v, w in the Cartesian coordinates. Okay, and delta ij is a notation which is equal to 1 for I equal to j. So if I is equal to j, then it's 1. Otherwise, it's 0. Okay. So, for example, sigma 1, 1 is nothing but xx because 1 corresponds to x coordinate. So I have a sigma xx. Is it clear what 1 means? 1 means x and x. That's what we used last time, and then I have to write everything. So to avoid that, I just use shorthand notation, and 1 corresponds to coordinate x, 2 corresponds coordinate y, and so on. And then I have minus p delta 1 1 plus mu du1 because I is 1, j is 1 plus du1 dx1. Okay. And due to the definition of delta function, we have this is 1, and then we have minus p plus mu, and the u1 is u, and x1 is x, which is nothing but minus p plus 2 mu du dx. Okay? And for example, sigma 1, 2 means sigma x, and 2 is y. And then I have minus p delta 1, 2. And then I have mu du1 dx2 plus du2 dx1. And since delta 1, 2 are different, so this guy is equal to 0. And therefore, I have mu. And then I have u1 is u, x2 is y. And then I have dv dx. Okay, so you can write, all the components that we discussed, last time, like this. So basically, we represent, stress. This is due to the, the pressure push each other, and also these are the, term due to the, relative motion between two fluid particles. So one could be, due to the stretching, and the other could be, relative motion in the tangential direction, this way, or that way. Okay, this is stretching, and this is friction. Okay, so after that we substitute this expression for stress into the linear momentum equation. Then we derive Navier-Stokes equation. And also we said if fluid satisfies this linear relationship between this stress and rate of strain, and then this fluid is called the Newtonian fluid. Okay, so this is true only for Newtonian fluid. But majority of fluid that you are going to look at, including for water, is a Newtonian fluid. And also there is the proportionality between stress and rate of strain, which is mu. And so this mu is called the viscosity. Okay? And more specifically, dynamic viscosity. Because this is, coefficient to write, the force or stress. Therefore, it is called, dynamic viscosity. There is another viscosity which we call kinematic viscosity. It's defined by the ratio between dynamic viscosity and density. Okay, and then we derived, Navier-Stokes equations. We end up with okay. So this is Navier-Stokes equations. This is true for incompressible fluid. Because we use, continuity equation at some point. And so when you combine this guy with this, then you have 4 equations for 4 unknowns. So unknowns are 3 velocity component, u, v, w, u, v, w, and p. Okay? So there are 4 equations, and there are 4 equations for 4 unknowns. So you can, in principle, you can solve the equations, but the difficulty that we have is that we have nonlinear term here. Nonlinear term means the product between 2 unknowns, and therefore there is no general the way to solve this system of equations. In the last lecture, I obtained an exact solution of Navier-Stokes equations with many assumptions, like so this is the problem that we looked at. So we looked at the flow over inclined plate with an angle theta, and then we assume there is a free surface here. To solve this problem, we have made many assumptions, like the flow is steady, time independent, and also we assume the flow is unidirectional, meaning that u is the only non-zero velocity component. We said v and w is 0 because also we assume it's a 2-dimensionality, so there is no dependency in y direction, and also therefore v is 0. With many assumptions, also we assume free surface is flat. So if free surface is fluctuating, that's what you see in reality, then you cannot solve Navier-Stokes equations. Okay. But with certain approximations or certain assumptions, you can find the exact solutions of Navier-Stokes equations. But the number of exact solutions for Navier-Stokes equations is very small. Only a few cases you can find the exact solutions. So practical applications, you cannot solve. You don't expect to solve this system analytically. So what you need to do is you have to do experiments, or you have to do numerical simulations. So that's what I'm going to describe a little bit. So that's today's topic, dimensional analysis. So let's say we want to know there's a problem, unbounded, there's no free surface and no bottom. And there's a sphere whose radius is, let's say, A. Or no. Whose radius is 0. Okay? And then you have a flow U here. So this is sphere. Okay. And this fluid, this sphere is immersed in a fluid, and fluid has its own property. So what kind of parameters do we need? We need density of fluid, and we need viscosity as well. Okay. Now, so we have a fluid whose density is rho, whose viscosity is mu. I gave you numbers for mu for air and water last time. So whenever you fix a fluid, then you already know mu at a given temperature. Okay, so in that fluid, we have a sphere sitting, and then we have a fluid coming in with a constant speed u. Now the question is, what's the force acting on this, this sphere? Okay, and let's call drag that force drag d. Okay, so this is drag. So that's what we want to know. Okay. So you might think, oh, why don't we solve, Navier-Stokes equations? But as I said, we cannot do it because, even this simple problem is too complicated for you to solve, the Navier-Stokes equations. Okay. So then you have to do, experiments, for example, and then you have to make a sphere and everything. But let's say you made the sphere whose diameter is 1 meter, big sphere. Okay. And the next time, suppose you have a different, radius of sphere, then you have to do experiment again. Okay. And in addition to that, you have to make another sphere to do the experiments to know the drag for the new sphere, which is a lot of work. What if you want to know the drag in air, in the air instead of in water? Okay, then you have to do another experiment. Okay, because the air has a different density and different viscosity. So the number of possible experiments that you have to do is infinite, in fact, and so you cannot do that. And so there should be a way to reduce number of experiments to find out drag acting on a sphere. Okay, that's why we need dimensional analysis. So what we know is drag is some function of all the parameters, like a velocity, rho, mu, and r naught. Can you think of any other dependence? Given fluid, given sphere? I think that's it. Okay. Of course, I assume the sphere, the surface of sphere is very smooth, very clean. Of course, in reality, there might be some bumpy, roughness, but we assume, we did really, hard work to remove all the, roughness. Okay. If there is a roughness, then that roughness has to be a function here parameter as well. Okay, but we say there is no roughness, then this should be the dependence. Also, I said it's unbounded. Okay, but as I said, there are too many parameters to find drag. So whenever you change u, you have to do the experiment. So whenever you change rho, you have to do experiment and so on. So there are too many parameters. I want to reduce the number of parameters. So to do that, what we need to do is so-called to use the so-called Buckingham's pi theorem. Let n be the number of physical variables and let's say k be the number of fundamental dimensions. I'm gonna explain what the fundamental dimensions soon. Okay, but let me state what this theorem says. Then there exists n minus k dimensionless parameters. So dimensionless is important. Parameters with which we can write some function f will depends on. So dimensionless parameters we call, or dimensionless variables we call pi. Okay. Okay. So let's use this example to explain what this pi theorem says. First of all, n is the number of physical variables involved the problem that you are interested in. So how many physical variables do we have? We have 1, 2, 3, 4, and drag 5. Okay? And I assume there is a relationship between those 5 physical variables for sure. When you change density, drag will be different, and when you change the radius of a sphere, the drag will be changed as well. So there is a certain relationship. I don't know the relationship, so that's why I wrote the f. Okay, but number of physical variables are 5. 1, 2, 3, 4, 5, and then k, number of fundamental dimensions, is 3. Okay. y. Earlier, I said, all the physical variables have, dimensions. You remember that? That's the, for what I talked about in the first lecture. And so here, for our problems, fundamental dimensions would be mass, m, and length, and time. Okay, those are the three fundamental dimensions that we will have. So, for example, last time, when I talked about dimension, the velocity has a dimension of length divided by time, because when you take a time derivative of a position, then you get the velocity, right? So you can represent the dimension of velocity in terms of L and T. Acceleration, you can write, the dimension of acceleration as L divided by T squared. Okay, so all the dimension of physical variables involved can be represented in terms of these fundamental dimensions. Okay. So this time I have three fundamental dimensions. So in this course our fundamental dimensions would be three, and then I expect, based on this theorem, I expect how many dimensionless parameters. 2. So n minus k is 2. So I expect 2 dimensionless parameters. Okay. I don't know what these are yet. And then I said pi 1. There is a relationship between this. That's what he says. Okay. We'll find out what pi 1 is, what pi 2 are, and then we can write this way. Or, equivalently, I can say pi 2 is equal to function of pi 1. Can I say that? This means, I can write this way. Or, I can write this way. It doesn't matter. So, for example, although this wouldn't be the case, if this is the relationship, then I can write this as pi 2 is minus pi 1 square, as I said here. Or I can write this as pi 1 is equal to plus minus pi 2 if pi 2 is negative. Okay? So I can write always in this way if I know the relationship between pi 1 and pi 2. You know what I'm saying here, okay? So let's see what pi 1, pi 2 are. So there are certain steps to get the dimensionless parameters, or which we call pi terms. Okay, so this we call pi terms. The reason why we call pi terms is the first guy who did this systematically. The first person who did this systematically was Buckingham, and in his work he used this symbol to represent dimensionless parameter. Okay, so this is the capital Greek letter for pi, and therefore people call these dimensionless parameters pi terms. But anyway, to find pi terms, what you need to do is first these are the steps. First, you have to list the number of physical variables. Okay. So what are the physical variables? Once again, for this particular example, d, rho, d, u, I'll use the same order. Rho, mu, naught. Okay. So you have to know what are the physical variables involved in the problem that you are interested in. And then choose k repeating variables which contain k fundamental dimensions. So for our case, k is 3, as I said. MLT are the 3 dimensions, fundamental dimensions. And you have to choose, the three physical variables, which we're going to use, repeatedly. Okay. So, but when you choose, the repeating variables, you have to choose, repeating variables which contain all 3 fundamental dimensions. So, typically what you choose is, let's say you choose rho. You don't have to do this way, okay? But then, this is an, usual way. I choose, the repeating variables as rho, u, and r naught. Okay? What is the dimension of r naught? It's a radius, L, right? So I need all MLT because those are my, dimensions. So this variable has L. That's good. The dimension of u, as I said, a dot means, dimension of this guy. Dimension of this guy is L divided by T. So I include T here. So I have to choose another variable which has, M as a dimension. Obviously, rho has a dimension M because rho is M mass divided by the volume, which is cubed. So by choosing these 3, I include 3 fundamental dimensions, which are L, T, and M. This choice is not unique. For example, instead of rho, I can choose either D or mu. Because D is a drag. Drag is mass times acceleration. So mass will appear there. So instead of you choose rho, I can use, D. But this time, I want to use rho because, rho is a property of fluid. Okay, D is what we really want to have. So D is kind of, dependent variable, and rho is independent variable. But, you don't have to do it. If you really want to do, you can have D. But the D is what you're really interested in for engineering applications. So I would not include, D as my, repeating variables. So I choose these three variables, which I'm going to use repeatedly, as you can see in the next step. So that's why these are called, repeating variables. Then third step is list the remaining variables, the dimensions of the remaining variables. So I already chose, 3 variables for repeating variables. So I have 2 left, and one is D, and the other is mu. I have to know the dimension of these 2. So let's look at it. As I said, drag is a force. So force is mass times acceleration. I have to write the dimension of drag in terms of fundamental dimensions, right? So I have M, mass, times acceleration. Acceleration is nothing but L, divided by t squared. That's the dimension in terms of my fundamental dimensions, okay, MLT. What's the dimension of mu? Do you know the dimension of mu? I don't know either. So we'll find it. So what is where did we get the mu? We got the mu from stress and rate of strain, relationship, right? So mu, so sigma was proportional to mu times, for example, du dx or du dy. It doesn't matter. Okay? We just want to know the dimension. So this guy is force divided by area. That's what the stress is. So stress times the area is force. So we know what the dimension of force, which is mass times acceleration. To get the dimension of stress, what I need to do is divide by area, L squared, is equal to, I want to know the dimension of mu. I know the dimension of u, which is L over T. Derivative means I divide by L. So far so good, right? And then we find the dimension of mu as this guy goes away, and I have what? M LT. M divided by L times T. Okay? That's the dimension of the dynamic viscosity. So that's what we have here. Okay. Then what? Then find, of course, pi terms. Pi terms such that the pi terms are dimensionless. Okay? So that's what I'm going to explain. Okay. Okay, how do we do that? This is the following. So I know there are two pi terms. So let me write pi 1 in the following way. I use rho u r naught my the repeating variables, and then I put power alpha, beta, gamma here, and then I multiply by the remaining variable d. Okay. The dimension of this guy has to be none. In other words, it has to be dimensionless. So I choose alpha, beta, gamma such that pi 1 is dimensionless. Okay. There is another dimensionless parameter, pi 2. I'll do exactly the same thing. But this alpha and this alpha are different. Okay, because and then the rest is mu. Okay, so just not to confuse you, let me put 1 here, just to distinguish alpha 1 from alpha, because these are different from this. Okay. So I'll choose alpha, beta, gamma such that we don't, these pi terms are dimensionless. So I use the repeating variables that we chose, which has the 3 fundamental dimensions, and then I use rho u r naught repeatedly here and here, and then I multiply by the remaining parameter like this. So for pi 1, I write the dimension of each one. We already know the dimension of rho, which is this, and then we have this. That's the dimension of rho, and the dimension of u is the L over T, and then we have beta here. And R naught, dimension of R naught is L gamma. And then drag, the dimension of drag is M times L over T squared. The dimension of this pi term has to be dimensionless, meaning that M okay? So let's look at M. We have how many unknowns do we have? Alpha, beta, gamma, 3 unknowns. So for M, we have alpha plus 1. That has to be 0. If I look at L, or T is easier, so let me use T first. Let's use T, and then I have minus beta from here, and I have minus 2. This guy has to be 0 as well. If I look at length L, then I have a minus 3 alpha and plus beta, and then plus gamma plus 1 has to be 0. So from here, I can find the alpha, beta, and gamma. So what do we have? So so this will give you alpha is minus 1, and beta will be minus 2, and then the gamma is what? 3 minus 2. Is that right? Okay. Plus 3, yep. Okay. And so we found alpha, beta, gamma. So now we know what the pi term, pi 1 is. So pi 1 is rho d divided by alpha is 1, rho. Alpha is minus 1. Beta is minus 2. And gamma is minus 2. Okay? So this is one dimensionless parameter. For pi 2, we do exactly the same thing. This is exactly the same. So this is rho u r. I use 1, but this time I didn't use subscript 1 to make it simpler. And then we have a mu, which is m over lt. Okay, this is what we got from here. And then if I look at m, once again I have alpha plus 1 is equal to 0. So alpha is minus 1. And if I look at the t, then beta minus 1 is equal to 0. So beta is minus 1. And L is minus 3 alpha plus beta plus gamma minus 1 is equal to 0. So gamma has to be 3, 2, 1, minus 1. Okay? So that tells you pi 2 has to be mu divided by rho u and mu r naught. So any questions so far? And then Bourgain's pi theorem says pi 1 is function of pi 2. Okay? So what is pi 1? Pi 1 is d drag divided by rho u square r naught square is equal to function of mu divided by rho u r naught. So now, here, drag depends on 4 physical variables. This time, this dimensionless quantity, which measures drag, is function of 1 variable. Okay. So, in other words, you can find d divided by rho u square r naught square you can draw a line like this. There is a certain, although I don't know what the f is. Okay, the functional dependence I do not know. You have to do experiments to find all these points. But all I can tell you is I can draw a single line that represents everything. Okay? So if you make, construct 2 pi terms, you do the experiments with a single fluid, and so rho mu you don't have to change. You don't have to make a model every time. You just use one model. All you have to do is just change velocity, for example, and then you change this guy. Whenever you choose a different u, you change this pi 2, right? Because you fix this, and you only change u, so you change pi 2 basically. So by changing one variable u, you change this whole thing. And every time you fix velocity, you measure drag, and then you compute this guy, and then you can find the point, and then you increase velocity a little bit, and then you find the point here. You find point here, 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 here. If you want to have another point, you can do several experiments, and then you can find this shape. Okay? Then, if somebody asks, so you generate this, graph by using water, and somebody asks you what is Dirac for the same, sphere in the air, it's okay. You know the rho, the radius, then you just use, the dynamic viscosity and density for the air, then you can find, point here, then you go up and up. That's a, Dirac that I will get. But if you really want to know the Dirac itself, then you multiply by, this value by this guy, rho times u times r naught squared. Okay? And also you can, if somebody asks, what if you have, 100 meter diameter, sphere, you can do exactly the same thing. So for example, ships, if you do the test using model test, and then you can tell everything, for the real ship by just computing, this parameter. Then you can, you can tell, what the drag is. If you don't do this, then every time you have to draw D, and then, for example, speed, you will get one curve. Of course, not this way. Drag will increase, okay? And then if you change radius, then you will get another curve. If you change the radius, you will get another curve, and so on. When you change in a fluid, you will get another curve here. There are so many curves that you have to generate. You can collapse everything into one single curve by using this Verkheim's pi theorem. Okay? That's what the dimensional analysis is about. Typically, this you probably know what this is. This is a so-called Dirac coefficient. Okay, so you write this way. Yeah. We haven't talked about it yet, and this is something called 1 over RE. RE is a Reynolds number. We'll talk about that a little later, but there is some name associated with that. So this is Reynolds number. Actually, a Reynolds number is defined by rho u r naught divided by mu. Okay, so this is 1 over there. So so from here we know. So what we know is, Dirac coefficient is a function of 1 over Reynolds number. Or I can say Dirac coefficient is a function of Reynolds number. Although the functional dependence would be different. Okay, but Dirac, if Dirac depends on 1 over Reynolds number, which means Dirac also depends on Reynolds number as well. Okay, so that's what we get. So basically, the curve that I draw is Dirac coefficient versus Reynolds 1 over Reynolds number. Actually, what I draw is one of the Dirac coefficient versus Reynolds number. Okay. So in the experiments, all you have to do is just change the Reynolds number by changing one physical variable, and then you will get the Dirac coefficients. After you make a table or graph, then you use that for many different cases. So this is a pi term, pi 1, and this is 1 over pi 2, of course. Okay. What if you use, the flat plate instead of a sphere? Okay, so you have some flat plate like this, and you have a flow coming in like this. So we have a fluid, so we still have rho, mu, and we are interested in drag, of course. And last time, I have a sphere, so I have only one characteristic length, which is a radius. This time, if I have a rectangular plate, then I have two characteristic lengths, right? One is length, the other is width. How many variables do we have? 1, 2, 3, 4, 5, 6. Instead of 5, we have 6. So n is 6 here. Fundamental dimensions are still 3, MLT. So how many pi terms do we get? So m minus k is 3. So I expect pi 1, pi 2, pi 3. I'll get exactly the same thing as before for pi 1 and pi 2. Which is drag coefficients and Reynolds number, right? So I will use exactly the same. I will use these three as my repeating variables. So this time CD is drag coefficient divided by rho u square L square instead of R0 squared, and Reynolds number will be rho u L divided by mu. Of course, you will get 1 over Reynolds number, but as I said, it doesn't matter Reynolds number or 1 over Reynolds number. Now, pi 3, you can do exactly the same thing. Rho alpha, u beta, L gamma, and W. You can do it like this, but you don't have to do it. This time it's so obvious what the dimensionless parameter would be. What is it? Pi 3 has to be dimensionless. That has to be W divided by something to make it dimensionless. So this time I have to look at the fundamental repeating variables L and rho u. And the variable that I should use, small l to not to confuse you, the dimension length l. Okay. So this time, obvious thing is, then I know this is dimensionless because this has a length. I should have a length here. Then it's a dimensionless. Okay. So you can go through like this. But sometimes you don't have to do it. Sometimes it's so obvious this is dimensionless. Okay? So now I can write drag coefficients as a function of Reynolds number. Not only Reynolds number, but also aspect ratio, which is W divided by L. Does it make sense? So of course, I have two parameters, so I cannot write as a single line. It has to be some surface, okay? Because it depends on two parameters. If you don't do this, then drag will depend on 5 different variables, okay? This time. But drag will depend on only 2 if you use, this Buchanan's pi theorem. Again, if you have instead of a flat plate, I can make, the problem, more complicated. I have instead of plate, I have a, box. Right? Then I have L, and I have width W. And then I have a height h. Then drag coefficient will depend on Reynolds number and W over L and h divided by L. Okay? And if there is a roughness, if this amplitude of roughness is A, then this guy will depend on A divided by L. Okay? So in many practical problems, there are many parameters involved. Of course, you can look at all these three, but you just look at the most important things that affects your problem. So quite often we neglect this, assuming that plate or the hull of ships are very smooth. Or sometimes we say, oh, this effect is small, and then we neglect this effect. Okay. So quite often when you measure resistance of ship, you just use the results of flat plate, which has the same weighted area. Okay. So is that clear? And so the most important thing is here is to identify what are the physical variables involved in the problem. Okay. Another example, let's say cylinder is moving up and down with a frequency omega with the amplitude A. So it's a cylinder is moving up and down with the amplitude. And so you have to specify frequency, right? But frequency is not enough. You have to specify how much this guy is moving. Okay? So you need these independent parameters. And since this guy is moving in a fluid, I have to, this problem will depend on density and viscosity. Is there anything else? 이거는 you took my last semester's class. Whenever I have waves, what do I need? This time, this guy is not moving. Okay, this guy is just oscillating, and that can be characterized by frequency and amplitude. There is one more that I need. Gravity? That's what I need. Okay? We'll talk about waves later in a slide briefly, but waves are the motion of free surface due to the gravity. If you don't have gravity, you don't have a wave motion. Okay. Of course, you have a surface tension as well, but surface tension for this kind of problem is small, and you typically neglect. But you can include surface. I don't know what the notation is for us, but the surface tension could be a issue. But for practical application, surface tension is not important. But all this. Is there anything else? Very good. So radius of a cylinder or sphere. What else? Submergence depth. And also we want to know, the force, let's say drag. So drag will depend on 1, 2, 3, 4, 5, 6, 7, 8 parameters. Okay, but some of them are not important. So when you change, surface tension a little bit, the result wouldn't change much. Then you neglect, surface tension. Okay. And typically, this kind of problem, viscosity plays a little role, so you then neglect, viscosity. Okay, but in general, you have to include, all this. Once again, from here, you can list, the dimensions of all the variables, and choosing, 3 repeating variables, and then you will get you can find, pi terms. So here, as I said, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 physical variables or parameters, and subtract 3, and you will end up with 6, pi terms. Okay. And I have to choose 3 repeating variables, which have dimensions of m, l, and t. What do you want to choose? We can choose rho, because that's a very fundamental property of fluid. What do you want to choose? Last time we used u, but this time I don't have u. So, but I want something which has a dimension of time, right? So you can choose g, or you can choose omega. That's what you prescribe. Before you start the motion, you have to tell the cylinder or sphere to oscillate with a certain frequency. So you can use omega. It doesn't matter. You can use g. You end up with the same thing anyway. And then the last one is we need some variable which measures characteristic length. So this is characteristic time and characteristic length. And this time, obvious thing is, okay, but you can use a, that's amplitude, and then you can construct the all pi terms as we did. So far so good. Now, so what if when you this is what you do when you do the experiments, but suppose you do numerical simulations, okay? Then what are you going to do? You have to use similar ideas, right? So going back to the first problem, sphere in a uniform stream, you cannot do the computations million times to cover whole the possible cases, right? So it's nice. We know drag will depends on Reynolds number. So all we have to do is just change Reynolds number, then find the drag coefficients. Okay. Then how do you do that? How do you get this relationship numerically? Experimentally, you just choose one sphere, one fluid. All you have to do is just change the speed of fluid, right, uniform stream, and then you just compute Reynolds number and so on. Computationally, you can do that. Okay, you choose any radius of sphere, and then you choose you just change the stream. But there is a more systematic way to do, which we call non-dimensionalization. Okay, so let me talk about non-dimensionalization of the Navier-Stokes equation, and then I'll come back to this. Okay. Oh, another, I forgot one thing. Okay. The thing that I forgot is dynamic similarity, which is related to this. So before I talk about non-dimensionalization, let me talk about this. So suppose you are interested in the drag of 100 meter sphere, and but you cannot do the experiments with a 100 meter sphere. There is no experimental facility which can fit 100 meter sphere, or you cannot have a experiments in the tank with a real ship. Okay, so you use the model, small model. Okay. So let's say you have the sphere. Let me use R instead of R naught. So there's a prototype, the sphere, and okay. So for example, if you want to know the drag of on sphere when you use 100 meters sphere in water with a speed of 10 meter per second, for example. Okay, and this is pretty fast one, fast stream and so on. You cannot do that, and so you use small model, okay, whose radius is Rm. So since you are interested in drag in water, so sure, why don't you use water, for example? You can do that. But it doesn't have to be water. You can have any fluid whose density is rho sub m. And then how fast did I have to move? I don't know yet. And let's say u sub m. So these are given. Basically, these are given, or it doesn't matter. Okay. You choose fluid, and you have a rho sub m. What you want to do is the following. You want to match Reynolds number. Of course, here not only we have a density, we have the viscosity as well. Once I fix in a fluid, so what I want to do is Reynolds number of the real sphere. I want to make the Reynolds number of model to be the same. Okay. Then from the Bourgain's pi theorem, what I know is has to be the same as this, right? Drag coefficient depends on only Reynolds number. So as long as you match Reynolds number, drag coefficient will be the same for both prototype and model. That's the result of Bourgain's pi theorem, because drag only depends on single parameter Reynolds number. Okay. So this is what you want to know. This is what you want to know. Drag over on 100 meter the sphere. If you know this, you can find this by multiplying by right. Once you know this, you can find drag. So once you know this, you know this. You can find this from here, model. This can be found, from here. So all you have to do is match, these two Reynolds number, and then you will get this experimentally. And then this guy is the same as this, and then you can find the drag. Okay, that's how you do how you make a model. So all you have to do is to make this match, and that will give you rho p u p r p is divided by mu p is equal to rho m um. Okay? If you use the same fluid, water for example, then what we end up with what? UP times RP has to be UM times RM. And then what? UM divided by UP is equal to, so this will give you UM divided by UP is equal to RP divided by RM. So typically this number is greater than 1, much greater than 1. You don't want to use 100 meter sphere. You use one small sphere, which you can make. 1 meter, for example. So this ratio is pretty large, which means you have to have a flow which is 100 times bigger than what is really happening in reality, which is not easy. So in other words, you have to move sphere very fast, or you have to flow which is very fast. Sometimes it's not that easy. Okay. But if you use air, you can do it. Of course, you change this, of course, right? But you can find that ratio in the wind tunnel. Okay. So instead of using the towing tank, for example, you might want to use wind tunnel to measure the sphere, the drag of the sphere. Okay. And so this is a real difficulty that you might have, but it's doable. It doesn't matter whether you have you have air or water. As long as you match these ratios, then you're okay. But there's one thing that I didn't talk about. When you have to be a little careful about using the air. Air could be compressible. Water is almost incompressible. You cannot change the volume, so you cannot make the flow too fast. Okay, and then compressibility plays a role, and so pressure is very large. Then volume can change. Then the flow in the air might be very different from flow in water, even though the ratio is the same. Okay, so but unless the speed is too large, you are okay. All right. So these are the scaling that you have to use when you do the experiments. And if you have drag, it depends not only Reynolds number. Drag depends not only Reynolds number, but also like a flat plate, right? Then not only you have to match Reynolds number, you have to match as well. So you have to match both, then your drag coefficients will be the same. So for example, if you have a 100 meter here, 10 meter here, if you want to reduce this to 1 meter, then you have to use, this one, 10 centimeters. Then the ratio is the same. Okay? So that's what this one. So often this calls, geometric scaling or geometric similitude, or this is dynamic scaling. Okay, for this match, and this match is called geometric scaling. Okay. I haven't gone, as much as I want to today, but anyway, I'll stop here, and then, the next Tuesday I'll talk about non-dimensionalization that I brought up. Okay. Any question? If not, see you next week.